Matthew is a data recovery engineer at DriveSavers. His specific focus is on data recovery from physically and electronically failed embedded flash memory in smart devices, utilizing SoCs and hardware encryption, as well as removable SSDs, flash drives, and other storage devices. He's part of a highly specialized and knowledgeable team of engineers who regularly push the limits of what is possible in data recovery. Matt has been working with NAND flash memory storage for 7 years. Before working at DriveSavers, Matt was a team lead of an electronics repair and IT solutions company. He began with DriveSavers in 2021, and with his team of data recovery engineers, continues to create new recovery methods that go above and beyond what was once thought possible. So with that, Matt, take it away, sir.
Good morning. Again, my name is Matthew Berger. I'd like to thank you all for attending today. This is something that some of the people in the audience have put a lot of time in. I'm very thankful for them for helping assist with the development of this. We'll just keep right into it. So I'm a flash physical data recovery engineer, meaning anything with flash storage, anything with an embedded chip on it. That's our department. That's where things go. There's rotational, and then we have flash storage. And so anything that suffers physical damage, and we see pretty extreme physical damage, especially in our data recovery industry, being smartphones. People are breaking smartphones left and right. I'm sure you know, I'm sure some of you have broken smartphones before. Here's just a brief overview of some of the flash memory devices that we see. This is just a small cross section. This is actually a table we put out when we're doing a tour live in lab. And as you can see on the left here, we have different Apple desktops. We have iMacs, we have Mac Studio. Some moving on to the right, we have some MacBooks, Microsoft Surfaces, iPhones, Androids, Android tablets, and all the way to the right where we have NVMe SSDs, SATA SSDs, and just raw NAND flash chips. So this is just really to demonstrate that we see so many of these consumer devices. Almost none of us really interact with devices with that much rotational media in them anymore. Everybody's phone is flash, everybody's laptop is flash. So that just kind of puts it into perspective. A lot of people walk in, that's what they first gravitate to. So I just want to get right in about the X-ray system. So the first thing is safety. People hear X-ray, they think, oh, scary, radiation. And this is a fully certified machine in the US and in Europe to operate safely. It can be operated by almost anyone. It's fully shielded. There's multiple interlocks, so that way there's no way X-rays are leaking out of this machine. A lot of people, they come for a tour, that's the first thing they say, is this safe to stand next to? Am I getting a dose of radiation by staying there? No, you can get right up on it. There's a small window, I think you saw this here. You can actually look right into it while it's operating, and they're fully safe. The other question is my data safe if I'm X-raying a NAND flash device? And this is based on some numbers published by IEEE. And it shows at the bottom here we have a scan from our X-ray system of one device. Then that's in comparison to the X-ray exposure that you get from a 6-hour flight. So you can see already that's not very much in comparison. It's very safe. Go ahead and move on here. And that is a chest CT scan. So that's what you're absorbing, your body's absorbing during one chest CT scan. They're usually measured a little bit differently. Biological X-ray damage is usually measured in Röntgen, where this is measured in rad, which is energy absorbed by matter when exposed to X-ray radiation. Move on here. And then this is 50 rad, so that's where your body starts to experience radiation poisoning if exposed to that in a short period of time. This is actually the legal limit for a lot of nuclear power plant workers in 1 year. So it's quite a bit of radiation. So this is where your body can start to experience radiation poisoning. So as you see, in comparison, if we look back at that scan of a flash memory device, it's getting very little actual energy, and this is thanks to a lot of things, mostly that this system uses about 3% of the energy output of a traditional X-ray system. This is not your traditional medical X-ray. This is something with a very, very low power output. And then this is the last one. So this is where, according to IEEE's numbers, a lot of NAND flash will start to have byte errors that are irreversible, or possibly damaged silicon. And so this is more the area in which we're looking for highly damaged devices. People have been told, there's a lot of things on online forums, oh, don't let them put your phone through the scanner at the airport. It's going to have data damage. And that is not true. This is very, very safe. Okay, so these are the first X-rays that we're going to take a look at. And this is something we'd see during recovery evaluation. So first time taking a look at the device, first time scanning it, we have on the left here some liquid damage. So the next two here, on the middle we have an SD card that has been irreversibly damaged. That's not a good recovery scenario, obviously. And then the one to the right here is just some minor damage to the corner of I believe that's a monolith style USB drive. So something where it's all the silicon and the package and board all in one epoxy packaging. Let's see. So, on the left, I just want to talk about, notice something that all three of these X-rays are in different sort of colored ways, different ways of interpreting density. On the left here, you're going to see that liquid damage with the very bright colors, and that's going to be a common theme with liquid damage. And it allows us to sort of look, in the middle of that X-ray on the far left is a chip. That's a chip that has some higher voltages in comparison to other parts of most embedded systems. So that's more like 3 volts. And you can see that, you can see each individual solder ball under that chip. And you can see how part of it is very consistent. They're all in perfect lines. They're all lined up very nicely. Everything's about the same density. Everything's about the same shape. Part of it, on the top right of that chip and sort of in the bottom left, you'll see there are missing balls. You'll see there is visible corrosion. You'll see that there's some signs that everything's not all right. So even on the outside of this chip, if you're looking at this just with your eyes, maybe it's been somewhere else, they've cleaned the surface level of the board. We're able to take an X-ray and say, that's not correct, that's where the liquid damage took place. And then just going through the middle ones, this middle X-ray I've chosen because it's actually a very good demonstration of the different layers of a monolith flash device. So you can see very, very distinctly the actual silicon parts of the device. You can see in the top left all that wire bonding is connected to the actual controller portion of this SD card. And then you can see where that break has happened. You can see the actual board portion where all the copper traces go. It's a good image to sort of just get an idea of what goes into an SD card. And then on the right, again, that is a monolith style USB drive. Got hit on the corner. There's a little bit of damage to the actual board layers going on there. That can be detrimental to the drive because if that happens in the right spot, some of those layers might touch. You're going to have power going from power lines to a ground portion. It's going to get very hot, possibly damage the packaging even further. So that's something we can identify very quickly. So just revisiting liquid damage, you'll notice that this picture is also in that same sort of color scheme. Now this is just because if you're looking on a monitor at grayscale, it can be hard to interpret density. You only have so many tones of gray, only so much contrast. This is some way that our eyes can see it as sort of a heat-mapped color system to be able to tell what is dense, what is not. And this chip here is actually a chip from a Macintosh logic board that is supposed to be 4 solder balls by 6 solder balls. And you'll notice, if you're very observant, which I'm sure you all are, that the ball in the top left of the chip is completely missing. It's completely corroded away by liquid damage. So even if we're looking at this and it's already been worked on, it's already been cleaned, and somebody says, I don't know why it's not working. This is a critical chip. This manages some of the voltages going to the embedded systems. We're going to need that to get data access. And that's not correct. You can tell actually where the liquid moved through on the left side, and the quality of those balls, even below where the missing one is, they're starting to deteriorate. They're not uniform shapes. They're not the right density. So that's an immediate sign of liquid damage. Here. Cracked silicon. So this is a USB drive that is monolith construction. It's been removed from its housing, and this experienced a bend and was heating up when it was attempted to be accessed. And you can look it on the left and say, well, it doesn't look that bad. There's no overt damage. What exactly is going on here? And you could spend a lot of time with a multimeter and using IR imaging or something, trying to figure out what's going on. And you may be able to deduce, oh, it was bent, we're getting heat in this area, there's a short, I can find it with the multimeter on one of these pads. There's probably some sort of internal short. But a few seconds in the X-ray machine, on the right, you can actually see it highlighted in there where the crack is going through. It's a little easier to see on sort of the top and the bottom portions of the drive because there's a little bit more, I guess, of a gap internally. But this is going right through the storage silicon. So some of those layers, again, are touching, power is going to ground lines, you have a full short to ground, and it's going to be getting very hot. And that's something that it would have taken much time to diagnose with a multimeter trying to figure it out. Maybe it can be taken care of one way. Maybe it's there's caps sometimes internally, capacitors inside of these drives. But this is immediately within 3 seconds, you're able to look at it and say, that's cracked silicon. All right, secure embedded devices. I'm just going to try to go through this part a little bit quicker here. There's more than just the storage required. You cannot take the storage chip off of an iPhone and then get your pictures off of it. And this is great for security. Companies like Apple and Samsung are fantastic at secure embedded devices that use hardware encryption, that use software encryption, that are paired diffuse arrays inside of their CPUs usually, to be able to be ensuring that you cannot just chip off one of these devices. This is not something that's really plausible. Move on here. So BGA rework comes into play. These are two CPUs that I've chosen because they look pretty nice, actually. The one on the left is an A15 CPU from an iPhone 13 Pro. The one on the right is an M1 CPU from a MacBook. And these are required to be able to decrypt the data. You can't gain access to it without these chips functional. A lot of times if the device is destroyed beyond repair and that chip is fine, we're going to need to be able to transplant that. And as you can see, there's quite a lot of solder balls going on here. There is, I believe, more than 2,300 solder balls that have to be perfectly recreated on the right side image there on that M1. It's no small task, and it takes a very skilled person, but you also want to be able to verify this. If, say, you transplant it, maybe it's still having the same symptom. Well, is it because one of those connections got joined underneath while you were soldering it, or is it something else? We're going to go ahead and move on here. Here's a picture that sort of demonstrates what you might see when you're actually inspecting VGA rework at this level. On the left, that's a Samsung Galaxy device. You can see the MediaTek CPU on the left side has actually a pretty complicated ball pattern. They're kind of all over the place. There's a lot of blank spaces in there that aren't very even, they're not symmetrical. And a lot of times if you're not putting this directly in its place when you're soldering down, it'll shift over slightly and you'll have one solder ball joining to another. It's not going to work correctly. So just for verification, on that right side you can see a VGA inspection done with the X-ray system. And it's a little bit hard to tell if you're not used to looking at pictures of electronics in an X-ray machine all day. But on the left, bottom left side of it, you can see some very even solder balls. You can see that they're all around the same shape, same density again. They're not joined together. There's not any solder bridges. I would look at that and say, oh, that transplant is very successful. If there's some sort of issue beyond that, it may be worth it to look into the actual CPU itself and the storage chip. So I just want to talk about continued R&D into chip level recovery. This is all what this is sort of building up to. So you saw the BGA rework, you saw the board components that we have tools to take off and put back on any of those components. But if there's something wrong with the storage chip itself on a deep level, or if there's something wrong with one of those chips required to decrypt the data, what are you going to do? This is becoming a bigger and bigger issue due to the fact that especially companies like Kioxia are making fantastic storage systems that are in one chip. They're great until somebody damages their device and they need that data off of it. They can back it up. So a lot of times we'll see this represented as debunks. So the wire bonds that actually bond the silicon to the outside world on the package of the controller are disconnected from impact or bending damage. You'll see electrically failed bonds where it's like burned out like a light bulb filament. These wires are incredibly small. They're fractions of the width of a human hair, and they're gold. And they're not soldered on, they're usually attached with ultrasound in the actual fab. So if enough electricity goes through that, just meaning just a little bit more than is spec, you have a burned out bond. Maybe the silicon is not damaged, but it can't interface with the outside world. So how do you go about continuing development into the recovery from the actual silicon? And this is sort of, on the right there I have a picture of, this is a CPU from an iPhone. I believe that's a A14 CPU, possibly. I don't exactly remember, I should have written it down. But there is going to be a whole toolkit moving into the future, I believe, of data recovery, moving into chip level recovery, away from the board level. That's something that there's a lot of information out there. You can get very good at it, and you can have very good success in recovery, but there's very little exploration into the chip level yet. And I just believe that we are going to see failure analysis techniques that are actually used in manufacturing moving into the recovery space. There's a lot of people who are doing great things with decapsulating, with chemicals and laser decapsulation. They haven't got to the point where you're not damaging the silicon yet, but there's a lot more research than there was years ago going into that. IR imaging, we're already doing great things with that, being able to see very, very detailed heat maps of tiny portions of chips and boards. And then, of course, micro-probing with micro-probing machines like they would do in a fabrication unit, as well as other failure analysis techniques. There's tons of information out there about that, but if something can be put together, it can probably be taken apart. And that's the next step, is how do you get into that chip, away from the board level, into the nano level of recovery. It's about my time. Thank you, everybody, for coming today, and back over to you, Troy.